어? 그러면 어때? Hello, everybody. Good afternoon. So, welcome back to DSP. So, today we are going to just continue our discussion on conversion between basically analog and digital signals. So, let me introduce today's agenda first. Okay, there are a few topics that I would like to cover, and the first topic. The first topic is to finish the lecture number 2. So in lecture number 2, in the end, I left one topic. Okay, so about the existence of DTFT. Not all signals can have DTFT. Okay, not all discrete time signals can have DTFT. So are there any sufficient or necessary conditions that guarantee the existence that we can calculate the Fourier transform? Okay, now, so existence of summation xn. So basically, we're asking what criteria are there so that yeah, if you chat, then it's kind of disturbing. Yeah. 请不要聊天哦，yeah, yeah. 请不要聊天啊，yeah. We'll be talking about what criteria there are for this sequence to converge, and this is our definition of DTFT, right? So it does not always converge, but there are some criteria to help us to tell whether or not the sequence converges for any omega of any frequency. So that's the first topic. And the second topic I'd like to introduce today is finally we can talk about conversion from discrete time back to continuous time. Okay, so in just roughly a symbol, we have a box, and we just write discrete to continuous, discrete to continuous conversion. And we need to know the sampling rate. The input is a sequence. The output is the result of reconstruction that we can denote as x of t, reconstructed, where R stands for reconstruction, 重建的, R stands for reconstruction. Reconstruction. Now you finish the spelling. So that's the second topic. And the third topic I think we do have time, okay? So I would like to finally talk about what do we mean to perform A to D, analog to digital. In this time, D stands for digital. Still, we need the sampling rate for sure. The input is a signal in time, and let's emphasize that it's continuous. The output now are numbers that's represented by in the format of in a format of every number here will be represented by a string of digits. Okay, let's say 0, 1, 1 something, 1. Yeah, so we'll use a number of bits. Let's say n bits, not n. L bits. So every number, when every number is represented by binarily in a binary format, there are a few issues that we need to consider. First of all, what kind of binary format is recommended? 我推荐使用什么样 is recommended? What format do we recommend to represent the real numbers? Signals are real, but when we have finitely many bits, how do we best represent all the numbers? So there's some certain issues over there. And secondly, so this idea, the key word is quantization. Quantization. In Chinese, sometimes quantization is translated to 量化. So how to represent real numbers by a string of binary zeros and ones, okay? So, and the kind of take-home message, or the most important message for us to understand is that whenever we apply quantization, quantization causes noise. There's a certain kind of noise called we call quantization noise. 吃东西的同学，我们讲过啊，开学就讲过啊，好吗？请大家还是彼此尊重啦，啊。开学讲过，上课不要吃。有隔壁间啊，可以去。You can go to the next room. For if you really need to eat. I don't oppose that. Okay. All right. So quantization introduces a kind of noise. Okay. So we'll talk about that. All right. So such is our today's agenda. Okay. Please don't. Worry, I'm not angry. I'm just. I've been teaching for more than 10 years. Okay, yeah, I understand. Yeah. All right. Okay, so today's agenda. All right. So first thing first, existence of DTFT. Okay, so this is on your. By the way, I heard that there's some issue with EE class, the system. I overheard you that you were discussing that you cannot log in. You cannot. That's bad. I'm sorry for that, but anyway, the lecture is going to be recorded, so hopefully for those of you that already downloaded lecture 3, you should be fine. Let's try, in another hour. Because the pre-note for lecture 4, which we'll talk about A to D and quantization, that pre-note has also been uploaded. So just late last night, apology for kind of loading up kind of late last night. But you will need that. You will need pre-note for lecture number 4. Okay. Okay, so today, let's talk about condition for existence of DTFT. Okay, so there are two criteria, one stronger criterion and another weaker criterion. The stronger first, okay? The stronger one goes if we say we have a sequence xn and we take the absolute value first, then sum. And if this summation converges, okay, because all the terms are going to be non-negative, right? So when we sum up, we say if this summation converges, it does not diverge to infinity. If it converges, okay? If it converges, then the DTFT x ej omega exists. Okay, it's a pretty strong. It's a sufficient condition. All right, the convergence of this sequence implies the existence of Fourier transform. It's pretty short. Okay, it's pretty, and it makes sense. And so there's actually a name for this kind of summation. When a sequence of numbers, real or actually real or complex, when a sequence of numbers, when we take the absolute value of a sequence of number and then sum them up, if that summation converges, we call that the sequence converge absolutely. Okay, in Chinese, it's called 绝对收敛, absolute convergence. This is a condition of that we call absolute convergence. If we first take the absolute value of a sequence of numbers and then sum them up, sum the absolute values, if that summation converges, we say the sequence converges absolutely. Okay, it's kind of funny when you say absolutely. Are you going to be on time? Absolutely. 我保证会啊，不会偷给你。But this is just a mathematical term. Okay, we say when this property holds, we say that the convergence is absolute, or sometimes we say the sequence converges absolutely. Okay, and there is a theorem in. If you have taken some advanced calculus courses, this is an important theorem. Absolute convergence implies convergence. Absolute convergence implies convergence. Absolute convergence implies convergence. So how do we utilize this fact? So the kind of a sketch of why this is true, why this property is true, is that when we think about now, we consider summation of xn e minus j omega n. If we consider this, right? If we consider this, taking this slightly modified thing, right? But then very soon you realize that xn, taking the absolute value of a complex number is equivalent to you can separate the two terms, right? Because when we multiply two complex numbers, their absolute value also multiply. In Chinese, 我们说复数相乘的话，这个绝对值相乘主副角相加。The absolute value of the product of two complex numbers equals to the product of the absolute value of the two complex numbers, right? So this equality is certainly true, but then what's this? When omega is real, e to the j omega n is just a point on the unit circle, right? So that is absolute value right there is equal to 1, right? So then we can simplify the summation. We can realize that, hey, the absolute value for the sum of absolute value equals to this expression. And if it converges, then summation xn e to the minus j omega n, then the summation of this sequence also converges. Yeah, the result is a complex number, okay, for any omega. Okay, that's kind of a sketch of proof. So we can convince ourselves that if a sequence back in the time domain, if back in the time domain the sequence converges absolutely, then in the frequency domain we can always calculate its DTFT. Okay? This is a strong condition, a pretty strong condition. Right. So that's the first condition. The second condition is what if not? right? Now we have a sufficient condition for Fourier transform to exist. But is the converse also true? The converse is not necessarily true. So I'm saying that for some signals, even though the signal does not converge absolutely, it's still possible that the signal we can calculate Fourier transform. We can define the Fourier transform of that signal. Okay? Should I repeat that? Right? The converse is not true. 反过来不尽然成立啊。It's possible. It's possible for a signal that we can define the Fourier transform even though the signal in the time domain does not converge absolutely. Okay? So a kind of a broader criterion is that if summation xn indeed, let me just loosely say it indeed goes to infinity, okay? But the signal is square summable, okay? But summation n xn square is absolute summable. If the square of the signal is absolutely summable, okay? Then it's kind of funny. Then DTFT converges in a special sense. Okay, let me repeat that. 就是在某种特殊的情况下 converge， 以某种特殊的方式 converge. DTFT converges in a special sense. What is that sense? Let me share with you. Okay, so I need my note, to make sure that I don't miss anything. Then x ej omega, then the DTFT, if we define it carefully, DTFT converges, then DTFT converges. So how do we define it carefully? It's a pretty subtle point. This is蛮微妙的. It's pretty subtle, but let me try. Then we first calculate finite sum. We can always do that. Then we first calculate finite sum from minus n to n. From minus n to n. This is a finite sum, okay? We first calculate the finite sum and then let limit n approach infinity. So if we just carefully define DTFT in such a way, and given that the signal converges absolutely, the square of a signal converges absolutely, and given this criterion, right? If this criterion holds, then this summation now defined as the limit of a finite summation. Okay. Now this summation exists, converges in the complex domain. The real part and imaginary part both converge. Okay. So we can define DTFT in such a careful way. This is a careful way of definition. And that is this way of convergence. This way of convergence has a name. Okay, we also have a name. That is, we say this x ej omega converges in the mean square sense. In the mean square sense. Okay. So these are like some kind of nice little knowledge that's not really helpful for your life. 我知道对人生不是非常有帮助啊。But yeah, for the sake of completeness, 为了这个完备啊。For the sake of completeness, I just introduced these two criteria to you. Right. So far so good? Yeah. So the second one is convergence in the mean square sense. Yeah. And Yeah, yeah, okay, yeah. So that's, there's something, you can see that it probably has something to do with Parseval's theorem. The Parseval's theorem is about summation of sum of square, right? So it probably it's related, but I'm not going to emphasize the relation, right? This property is probably related to, let me say, just a reference. You can refer to Parseval's theorem if you ever want to ponder what's going on. Parseval's theorem might be a good reference. It's good to reflect about Parseval's theorem at this point. If a signal converges in the mean square sense, then its Fourier transform can also converges if we define it carefully. This is a careful definition. Okay, careful definition. Right. Okay, so I'd like to close this lecture right here. Okay, this is the end of lecture number 2, in which we learn about a lot about DTFT, all the properties, DTFT, shift theorem, convolution theorem, Parseval theorem, and so on. Okay, and And in the end, now we just, for the sake of completeness, we introduce a criterion for DTFT to exist. Okay, later we'll come back to deal with signals which does not have DTFT. Okay, maybe as a kind of preview. Then what if DTFT does not exist? Is there another tool we can use to still analyze the signal and its response, and so that as an extension to DTFT, then in the next chapter, in chapter 5 of textbook, we will introduce Z transform. It turns out that Z transform is a generalization of DTFT. So we can have a broader class of signals in which we can talk about its Z transform, okay, on a complex plane. So the related topic, kind of extended topic, kind of a preview. So now we are ready for chapter 5. Okay, extension is Z transform. So we'll cover that in chapter 5. All right? Yeah. So let's close this lecture. Can we? Let's close this lecture and move on to the next topic. The next topic is I'm hoping, to let's take a break for 2 minutes, okay? Yeah, but I might need to copy my note into, duplicate my note so that I can reuse my pre-note next year, okay? So I might have forgot to do that for lecture 2. All right, so let me figure out. I want to duplicate this, so next year I can reuse the pre-note. Okay. All right, so, okay, so yeah, less than 2 minutes. I finished duplication in 20 seconds. Right. Any question regarding the existence of DTFT? Right. It's pretty subtle. Yeah, it's pretty subtle, especially the second one. Second one might look like 废话, look like garbage. But I'll let you figure out. Okay, it's pretty subtle. I agree. It's pretty subtle. No. But our next topic, okay, so finally, lecture number 3. Now here we talk about D to C conversion, and the key idea is low-pass filtering. Low-pass filtering. When we convert our sequence of numbers in the digital domain back to analog or back to continuous time, there is a place where we need to introduce low-pass filtering, an ideal low-pass filter. Okay, ideal low-pass filter. So in this lecture, we will briefly explain what that low-pass filter looks like. Okay, in the time domain, and it turns out that when we apply low-pass filtering, we introduce smoothing, a kind of smoothing or interpolation to change from discrete sequence to a continuous, back to continuous time. Okay, so how does that happen? So recall that, so here's a bit of recap. So recall that in the beginning we have a continuous time signal, and then we take its samples, right? We measure the continuous time signal every so often, okay? We take a measurement at every sampling period. And then we take the Fourier transform of the result. We have repeated copies of the spectrum, which looks symmetric. Repeated copies of the spectrum, and which shows up at multiples of 2 pi divided by sampling period. Okay? Yeah. The spectrum repeats itself, and we have also talked about a requirement. We recommend that our sampling rate to be high enough, right? We recommend our sampling rate to be high enough to avoid aliasing. So even though that we have repeated copies in the spectrum in the frequency domain, as long as they're well separated, they're separated far away sufficiently, then there's no interference. There will be no interference between these copies. Okay, so the idea is that in this figure we just already implicitly assume that omega n, which is equal to half of the sampling rate, which is equal to pi divided by t. Okay, we require this to be greater than 2 pi times a bandwidth. Yeah, that's a requirement. That's our recommendation. We recommend that the Nyquist rate is greater than 2 pi times bandwidth. So this is actually the bandwidth here. That's 2 pi times bandwidth. Okay. Here, right? So if we sample at least 2 times higher than the highest frequency, that's the idea, then these aliasing does not overlap. These spectral copies, they do not overlap, and we are fine. We are just fine. Okay? Why? Because then, in order to retrieve just the middle one and reconstruct the signal back in the time domain, in order to go from discrete time back to continuous time, we can just apply an ideal filter. The idea is that we want to apply an ideal filter which has a cutoff frequency at our Nyquist. Okay? The idea is to apply a filter, let's call it H of big omega. Okay? The idea is to apply an ideal filter which has a unit gain. The gain is flat gain, equal gain for all frequencies in the passband, but the gain equals to 0 outside the passband. If you can just apply this some simple filter, then in the frequency domain, only the middle part will be kept, will be preserved, while we reject all the other extra copies. Okay, so applying the idea is that we want to apply an ideal low-pass filter. Okay, the ideal low-pass filter. So here, this is my answer. Just conceptually, if we sample the signal fast enough, then conceptually we can use a low-pass filter. Conceptually, you can use a low-pass filter to reconstruct, wrong button. This button. To reconstruct the signal in continuous time from its discrete samples. That's the idea. We can use a low-pass filter to reconstruct the continuous time signal from its discrete samples. Okay? Yeah. So far, so good? Yeah. Okay. So here, to kind of develop our concept further, what's going on here is that the discrete sample may look like a sequence of impulses in the time domain. A sequence of impulses in the time domain, okay? And we have an expression right here. We have an expression of a signal after being sampled, right? We have used this notation a few times by now. So we use this expression to represent the signal after it is sampled. Why? Because we have converted the signal into a sequence of impulses, and each impulse is scaled, the height is scaled by discrete samples, by the sample value. Okay? So this is the expression of the signal after sampling. Okay? And in the time domain, it looks like a sequence of impulses, and the height, the value of the impulses could be positive or negative depending on, actually some just equal to the sample values. So far so good? So that's a representation, one way to represent what's going on after a signal is sampled. Okay? After a signal is sampled, this is the result. And when we say applying a low-pass filter, we need a kind of an accurate definition. Okay? So here's the definition. We want to convolve our signal with an impulse response in the time domain. Okay? But here we're drawing a box, which means the low-pass filter. The low-pass filter. So this is the low-pass filter right here. The low-pass filter right here. So we will turn the signal, a sample version of the signal, back to a continuous time signal right here by applying a low-pass filter in the middle. So the low-pass filter, if you have taken signals and systems, here we are talking about continuous time. Okay, so we know that multiplication in the frequency domain is equivalent to convolution in the time domain. Okay, so when we say low-pass filter, in the frequency domain, we multiply the spectrum with the frequency response of the filter. In the frequency domain, there is multiplication. But back in the time domain, we have convolution of the signal with the input with the impulse response. Okay, is that clear? Frequency domain multiplication. Why? Because low-pass filter, let's say this gain is 1 in the passband and 0 in the stop band. Okay, that's an ideal situation. Okay, so by doing that, we will just perfectly keep the middle copy that we want, while perfectly rejecting any extra copy elsewhere in the frequency domain, right? So that's our idea. That explains why we are multiplying our spectrum with an ideal low-pass filter. What happens in the frequency domain is multiplication, okay? But back in the time domain, we will have convolution of our signal with the impulse response of this filter. Okay? Now, so far so good. Convolution in the time domain, right? And when we say impulse response, is the important concept goes here. Impulse response is simply the inverse Fourier transform of the frequency response. Impulse response in time, frequency response in the frequency, and they form a Fourier transform pair, right? So we can take the Fourier transform of the impulse response of system to the frequency domain, then that gives us a frequency response. Or we can go back to time domain by inverse Fourier transform. Okay, so with some detailed derivation we will show later, turns out that the inverse Fourier transform of ideal low-pass filter is equal to this function, which looks like having sine on top, sine of something on top, and that thing also shows up for the denominator, 分母 or denominator. The factor of pi t divided by t. Pi t divided by sampling period. This factor, same factor, shows on top and also at the bottom of this expression. 上面下面都出现了. This function is the inverse Fourier transform of our ideal filter, of our ideal frequency low-pass filtering response. If we take the inverse Fourier transform, it gives you, we can show in a moment that this is the result. Okay, this is a result. We'll show the derivation later. We'll push that later. But at this time, at this moment, I want to invite you to take a look at this function. Let's all take a look at this function and make a plot, shall we? Let's make a plot of this function. What do you mean dividing sine pi t divided by sampling period? Divide this term by that. What will happen? Okay, what will happen? Any suggestion as to how to make the plot? Okay. To make this plot, first we can notice that there's sine, right? Sine on top. Sine on top, so we expect this function, this impulse response, to cross zeros, to have zero crossings. Sine, right? So it should have zero crossing right here when pi t divided by t is equal to n pi, right? Is equal to integer multiples of pi, then we have sine of that is 0. You all know what I mean, right? So turns out that this when t equals to big T, that's our first zero crossing. Okay, the first zero crossing occurs at t, and also then we have a second crossing at 2t, and so on. Okay, and so on. So we have zero crossing at integer multiples of t, 3t. Let's even draw a picture extended to 4t and so on. So we expect to have zero crossings. And the function is also symmetric. It's an even function. 是个偶函数. This function, this impulse response is also an even function. So we expect to have a zero crossing at negative t, negative 2t, and so on. And so on. Okay? It's going to be symmetric. But then what happens at t equals to 0? At t equals to 0, we need L'Hopital's rule, okay? L'Hopital 法则. For those of you that attended one of the sessions last week, I'm glad somebody mentioned L'Hopital rule. Yeah. Okay. Turns out that HRT is equal to limit t approach 0 sine pi t divided by t divided by pi t divided by t. And when you apply L'Hopital's rule, we know that sine x approximates x at small x, right? So the ratio is what? The ratio is 1. This limit goes to 1. Okay, this limit goes to 1. Okay, so we have a simple kind of, we set a few anchor points, 我们把一些锚点, some important points. We have found out how to evaluate this expression, this impulse response. It approaches 1 at time 0, and it's equal to 0 at integer multiples of sampling period. So just to connect the dot, and also note that there's a t at the denominator, 分母的部分. Denominator, we have t shows up right there. Therefore, another thing to notice is limit t approach infinity, this impulse response is equal to approaches 0. The limit approaches 0 when t approaches infinity. Actually, plus or minus infinity, both. So we have an oscillating signal, which decays like that. So it has an envelope. So let's draw a picture. Let's finally draw a picture. So the function may look like 1 here, 0 here, and then another 0 there. So we expect it to look like something like this. And the amplitude becomes smaller and smaller. And in the end, you can imagine it approaches 0 at infinity. Okay? And same thing also happens on to the left. Here, 0 crossing, second 0 crossing, third 0 crossing, and so on. And it also approaches 0 at t equals to minus infinity. Okay. So far so good. Now, so this function is the inverse Fourier transform of our ideal low-pass filter. Right now. So this function has a name, by the way. This function is called the sinc function. Yeah, the sinc function. It has a name. Sometimes people even denote the signal as sinc. Okay, it's called sinc function. Sometimes we can refer to this function as sinc function. So the inverse Fourier transform, as we will show later, the inverse Fourier transform of our ideal low-pass response is the sinc function. Okay, and as I said that now we have this impulse response, and we are going to show what's going on in the time domain when we send our signal. When we send our sequence of impulses to ideal low-pass filter, what will happen in the time domain? Can we visualize this, the effects? And that's what I want to demonstrate next. Okay? I want to demonstrate that when we convolve this impulse response, when we convolve this impulse response, when we use the impulse response to convolve with our sequence of impulses, what's going on? Yeah, what's going on? What's going on? Okay, so what's going on? We are going to convolve our signal right here, which is denoted as a sequence of impulses, right? But then we need to convolve it with sinc. Okay? It turns out that we can develop this one step further. Okay, 再往前一步啊。We can develop this one step further by what? By putting the sinc function inside the summation. You know, because convolution is a linear process. Okay, convolution obeys linearity. You first sum up, then convolve. That equals to first convolve, then sum up, right? So we can develop this further by putting the sinc function inside the summation, and let's see what will happen. Okay? Now, so to further develop this idea, let me move my notation around. Yeah. I like to cut it and move it right here. Okay. So I'm going to put that into the summation. So summation is still here. Xn times delta n minus t convolved with sinc. Okay, sinc is simply our impulse response. And now let me put the bracket around here. Put the bracket around there, right? Why not, right? We can do that. Putting the convolution inside the summation. And what do you notice? Oh, by the way, sorry, did I say n minus t? No. T, this is wrong. Yeah. Wrong here. Yeah. Not n minus t, but t minus nt. Okay, yeah. This is wrong. T minus n times sampling period. Okay, that's the expression. Yeah. So there's a correction rate, but they're here. after we put the convolution inside the summation, then I want you to look at this. We are now having a convolution of a function with the delta function shifted to nt, right? What's the result? When we convolve any function in a continuous time with an impulse which shows up at a particular time, then we are simply moving that function to that time, right? Shift theorem of convolution. Okay? So now we can simplify this expression by saying that this is nothing but summation n xn, and I'll stop here. That function shifted to time nt. This is the expression that I want, okay? That we want to use, okay? This is the expression. This is what's going on when we apply low-pass filter to a sequence of impulses. This is what will happen. We will have the sinc function right here, but shifted and scaled by the sample value, and we sum them all up. We overlap and sum them all up. Sum up all of them, okay? So let's work together. What's going on, okay? By taking an example, right? What example? So let's say we have this example of a signal, like a sequence of samples in the time domain. They are just a sequence of samples. And then what we are going to do next is to apply this formula to understand what happens when we send this sequence impulses to a low-pass filter. Okay, we'll see what the low-pass filter does to our sequence of impulses. What kind of effect? So here, in this expression, we will put what color? Yeah. So let's focus on this particular sample, for example, right? For this particular sample, we have, note that if this is t, this is 2t, 3t, and so on. So this we'll have a copy of the sinc function, but the sinc function, the nice thing is that it crosses 0 right there, and it crosses 0 right here. Okay, let me actually really put not dash line, 不要用虚线，直接用let me just directly put a solid line right here. Okay, and also it extend in the negative time direction to minus t. So we have a copy of a sinc function right there, and its height is adjusted to x of 1. That's the height. Okay, we're moving a copy of the sinc function to time 1. And similarly for time 2. For time 2, let me put another color. Okay, how about purple right now? We have a copy of the sinc function which is adjusted, the height is adjusted to the value x2, right? And there's a sinc function, and it nicely crosses 0 at all other times right there. And it nicely crosses 0, and so on. So that's our second copy, and be careful, it extends infinitely. Okay, it's a sinc function, but a second copy of a sinc function. Okay. Now, how about this negative sample right here? This sample has a height of x3, which is negative, right? But yeah, regardless, we can still put a inverted sinc function, 把它倒上下倒过来, inverted sinc function right there, upside down, right? So here we have a copy of sinc function which nicely crosses 0 at the neighboring points, and then something like that. Something like that. That's a negative copy of the sinc function. Okay, shall we move on? Yeah, shall we keep doing this? So imagine you keep doing this, keep doing it and doing it. Okay, so we just if we just keep doing this, the fourth copy that looks like that, smooth, and so on, and so on. And the fifth copy, then here, larger. It's here, and here, and so on. And sixth copy, and so on, and so on, and so on, and so on, right? And then in the end, we are going to add up to sum all the infinitely many copies of the sync function. That's what's going on. That's what's going on that's what our low-pass filter does to the signal. That's the effect, okay? In the time domain, we will be, by the sketching, we'll see that we have all the sync functions, they overlap in time. But nicely, they all have the zero crossing in neighboring points, okay? Yeah. So as a result of summation, now we can finally talk about summation. As a result of summation, I hope that we can imagine, okay? Use your imagination to see that this effect is really smoothing. Now, we have a smoothed signal, okay, when we sum up all the sync. When we sum up all the sync, we have a smooth signal. Now, when we sum them all up, we have a smooth signal that crosses here, 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 and here, and here, and here, here, here. We are smoothing the signal, okay, as a result. Consequently, low-pass filtering really is all about smoothing. It's a way to smooth our signal, okay? Or let's take a break. Okay, yeah, let's take a break. So this is what's happening when we apply low-pass filtering in the time domain, okay, by convolution. Right? Let's take a break of 10 minutes.
就我觉得这个机出来，就我不知道为什么是这个，就是我机出来它没有大题。
好像吗？对，所以你是正确的。我们最后其实这个 gain 蛮 tricky，这个 gain 不可以是1了。我刚刚是会议没有特别强调，那个 gain 如果你设 gain 等于1的话，就会得到的确会得到会差一个 factor。对，会差一个 factor。其实你是正确的。
所以就只是它这个只是说出来，它是一个 sync， 只是再加一个常数而已。
其实还会有个常数。OK。
然
后那常数也许不是常数。
OK， 好，谢谢教授。
我之前有点忘记那个。
Okay, I need to change battery. 换一下电池啊。Hello，OK，好，那一样，上课时间请不要吃东西啊，在这间教室里面啊，请不要吃东西啊。还是说学校应该多开一些餐厅？Maybe. I know, yeah. Lunchtime is always short. All right. So how do we have here? Sync function. Okay. When we just sum up all the sync functions, then we get back a signal in continuous time, and it is smooth because that's what low-pass filtering is giving to us. So a continuous signal, smooth, but also this idea is interpolation. Okay. So interpolation, 内插 So sometimes low-pass filtering is called sync interpolation. So essentially, we are performing a kind of interpolation, not impo. We are using the sync function for interpolation. So therefore, this action is referred to as sync interpolation. Using the sync function for interpolation. Interpolation in Chinese is 内插 Extrapolation is 外插 interpolation 内插 So really just to kind of sit back and contemplate on what's going on. What's going on is that we have a sequence of samples which happens in discrete time, okay? Discrete time. And then we need to figure out to construct a continuous version from samples, right? So essentially, 本质上, essentially we need to fill the blank. Yeah, we need to fill the blank between samples, yeah, which are unknown, right? Between samples, we don't know the value, right? So essentially, when we figure out the values between samples, that's an action of interpolation, 做内插, right? For example, if my 我用中文讲一遍哈，比方说，如果我们身高在国一的时候160公分，国二时候、国三时候170公分，请问我国二的时候几公分 ？Missing information, right? Let me explain why. So let's say if my height is 160 centimeters when I was 11 years old, and my height becomes 170 when I was 13 years old. The question is how tall am I when I was 12 years old, right? Missing information in the middle. That's essentially what's going on here. We have discrete samples, but in the middle, everything's missing. So we need to interpolate. We need to make educated guess. We need to guess the values. We need to guess out the information, the missing information in an educated way. And in this case, our educated way is to use the sync function for interpolation. So we can reconstruct a continuous signal from its discrete samples. So essentially, this is what we are doing, using the sync function for interpolation to figure out the missing information. And we know that sync function corresponds to low-pass filter in the ideal low-pass filter in the frequency domain, right? Okay, so with that, like to just briefly mention this, the overall kind of architecture of digital signal processing, right? This figure is pretty simple, and it corresponds to textbook section 4.4. So if you're interested, please refer to the textbook 4.4. So the overall architecture of all digital signal processing may involve a few steps, okay? The first step is to go from continuous time to discrete time by taking samples. So this is a summary. Xn is defined as the signal evaluated at n times the sampling period, okay? And then in the middle, we process the signal in any way we want, okay? So let's say yn is the result after processing. There's this big question mark here is any processing, okay? Let me maybe say any processing you can imagine. So any processing you can imagine, and then in the middle, and then the output, this becomes the output sample. Output samples. Then we apply D to C conversion by what? By convolving the impulses with sync, by performing sync interpolation. By performing sync interpolation to get back to the continuous time domain. Okay, so again, here the notation goes small n and small t. Small n is discrete time, small t is continuous time. Okay, yeah. So that's the overall architecture, overall working flow for all digital signal processing, coming from continuous time to discrete time and process signal in the middle and produce an output. Okay, so that's all about digital signal processing. So later in chapter 5, from chapter 5 and on, we will focus on the middle. Okay, how do we process the sequence of numbers? How do we process the samples? And with kind of confidence that we know how to, at least ideally we know how to perform C to D conversion and D to C conversion. Yeah, so that's the overall architecture. Okay, but before we leave this lecture, I want to just invite you to make the derivation together. So we want to see indeed that the inverse Fourier transform of low-pass filter equals to sync function. Okay, so let's work it out together. Yeah. So here's the deal. Let's say we have a low-pass filter. A low-pass filter which has such frequency response. Okay, let's say the frequency response is constant. K stands for a constant. Okay, let's say the frequency response is constant K, constant gain for omega smaller than Nyquist rate for the passband, and 0 elsewhere. Okay, this is an ideal low-pass filter, perfect constant gain for the passband and perfect rejection for the stop band. Okay. And now simply we take the inverse Fourier transform. We'll simply take the inverse Fourier transform, which is by definition goes this way. Yeah? This is nothing but just a definition. Okay, so still just copy 1 over 2 pi. And how about this integral? In the frequency domain, the integral now should go from Nyquist rate, minus Nyquist rate to Nyquist rate. Half of the sampling frequency, okay? Where the gain equals to K, Ej omega t d, and this integral is with respect to the frequency, okay? Yeah. And then just simply still copy 1 over 2 pi. Here, to make the integral, we know that with respect to omega, then we have jt 1 over jt e j t omega, where omega is evaluated at plus Nyquist rate subtracted by minus Nyquist rate, okay? Minus of negative Nyquist rate. So let's still develop this further. 1 over 2 pi is copied here. JT here, and this is EJT omega s divided by 2 minus EJT minus omega s divided by 2. Okay, so that's the result. This is a result of performing a simple example of performing inverse Fourier transform by integral, okay, by integration, by calculating an integral. Yeah. So let's still copy everything here. So it doesn't look like a sinc function yet, right? This does not entirely look like a sinc function. But here, note that e to the j something minus e to the its conjugate, this equals to 2j times sine of what's inside t omega s divided by 2, right? This is kind of an application of Euler's formula, okay? We have a complex number minus which is subtracted by its complex conjugate. The result is 2j times its imaginary part. Yeah, okay. So now we can do some cancels in j, cancels j right there, and probably 2 also cancels 2 right here. So now we have pi t in the bottom here 1 times sine. What is omega s divided by 2? Omega s equals to 2 pi divided by sampling period, right? So here we have pi t divided by t. Okay? Yeah, that's the result. Oh, I'm missing k right here. So everything now we have a constant k, constant k, constant k, constant k. Okay, that's the result of applying of the inverse Fourier transform. The inverse Fourier transform of our ideal low-pass filter, which has a gain of k for the pass band. Okay, a constant gain of k for the pass band. 大概是这个样子啊。So that's a complete derivation. Okay, so now simply, if we choose k equals to big T, then the inverse Fourier transform is what we have. Okay, now that's a matter of just scaling. Scaling the function, if we scale it, you choose a gain to equal to constant t, then we have the inverse Fourier transform, which equals to the impulse response. Then it equals to sine pi t divided by big T divided by the same thing. Now, after some rearrangement of terms. Moving the terms around, you can verify that this is true, and we finished our derivation. Okay, now, it's actually not hard. You can work it out. Okay, I believe that this is quite straightforward. Okay, so but the important thing is that later, right? So just please refer to the textbook if there's any question. But really, we will just use this kind of overall structure for processing continuous time signal in the discrete time domain. Okay, know that the input is analog continuous time, the output is also analog continuous time, but we process the signal in the digital or discrete time domain. Okay, that's the kind of spirit of all digital signal processing. Mostly, this is what we are doing. All we are doing is to process continuous time signal in the discrete time domain. Right? So everything now becomes filtering and so on. So we will be covering, we will start our discussion of processing, the processing part. That will be next chapter. Okay, chapter 5. In chapter 5, we'll talk about we'll start with examples of how to process our signal in the discrete time domain. But keep this in mind. Next, I'd like to go to our final topic for today. Okay, we've been talking about discrete time, and I emphasized previously that we are not yet in the digital domain. Not yet, because we are not yet talking about how to represent our signal by binary numbers. Okay. Now we all need to do that because to process signal in the digital domain, all the numbers have to be represented somehow. Okay. Have to represented somehow as binary numbers, as a string of binary zeros and ones. Okay. So, but in doing that, inevitably, inevitably, we introduce noise because there's loss of information from continuous to when we quantize our signal, okay, in the binary domain. So we will just now we are ready to enter our next lecture here, and again, let me just duplicate it so I can reuse it next year. Okay, all right. So here, this comes our next topic. Okay. So in this lecture, this is actually a set of PowerPoint slides. Okay, right? Yeah. We are going to introduce, finally, introduce digital processing of analog signals. Okay, and so this lecture really is a highlight from materials in section 4.8 of the textbook. So that's a reference you can take a look at when you go home. But digital processing, finally, we're talking about representing number. We'll be talking about representing numbers as zeros and ones. And next slide here, the first plot is simply what I just mentioned to you, the overall structure of processing continuous time signal in the discrete time domain. Okay, so the idea is that we have continuous time signal, and then we use a kind of C to D converter with sampling period to go to the discrete time domain, and now we have our signals become sequences of numbers. Okay, a signal becomes a sequence of numbers, and then there is a system which produces output, and the output is still a sequence of number. And then from there, we apply sync interpolation, at least ideally, to get back to the time domain, to get back to analog. Okay. But this might be a kind of oversimplification. 太过简化. This picture is a bit too simplified. So the a more complete picture is this chain of processing. Let's go over this chain of processing, chain of different steps. Let's go over it for the first time. Okay, so there are a few practical issues. Practical issues to consider is that there are at least 3 issues we need to discuss. The first issue is that continuous time signals are not precisely band limited. Okay. Taking the sound, the acoustic signal, the 声学 acoustic signal right here, right now, as an example. Of course, you hear me talking, right? But chances are there might be a kind of some ultrasound. 有一些超音波 There might be some ultrasound signal also present in this environment. It's just not that you cannot hear it, right? The audio, the acoustic signal might be not exactly band limited. Let's say there's a bat, right? 如果有只蝙蝠的话, or a dolphin. Here we don't see a dolphin, but yeah. Animals can make ultrasound signals, right? So in general, the acoustic signal itself might not be precisely band limited, okay? So usually what we, to be careful, even before we start sampling, this is sampling, okay? Before we start sampling, we want to apply an anti-aliasing filter. Okay, an analog filter. That's the first step. How to reject the ultrasound, for example. Even before I start recording my voice using this microphone, somehow there must be an analog filter which rejects ultrasound. There must be. Okay, seriously, there must be. Okay, it might be just this microphone itself mechanically, its response is band limited, or you apply this low anti-aliasing filter electronically, either mechanically or electronically. We need to reject the ultrasound. Okay, and that's what anti-aliasing filter is about. Yeah. Okay, so and then we talk about some practical issue, to convert our continuous time signal into a sequence of impulses, and then represent it binarily. Okay, so generally we can imagine two steps. The first step is called sample and hold. Second step is analog to digital conversion. Okay, and we talk about that. And then this is chapter 5. Okay, I can just be sure this is not yet. We are not yet going to talk about discrete time systems. This is a topic of chapter 5 and 7. Okay, 5, maybe 5, 6, and 7. We'll finally talk about processing. But then after processing, when we obtain the output, then we apply a D2K-A conversion. This is the part I would just leave it to you as like you can study it as this is extra material. I'm not going to test you on that. Okay, extra material. So today we are not really going to talk about D to A conversion, but rather I want to talk about quantization, A to D conversion, and why this inevitably introduces noise, quantization noise. Okay, this is the main topic I want to focus. Okay. So that's a few issues I've mentioned. That continuous time. The first issue here. The first issue is that the signals are not precisely band limited. Therefore, we need anti-aliasing filter. Okay. Second issue is that it turns out that ideal low-pass filter cannot be realized. This is funny. Okay. Ideal low-pass filter, as we just introduced in the previous hour, D to A conversion. Right. I was recommended to apply an ideal filter, but ideal is ideal. Nothing will be ideal. Okay, and one thing for you to notice that you notice the impulse response, the sinc function, it lasts forever. In both negative time and positive time, sinc function has infinite ripples. It goes from minus infinity to plus infinity. So it's an ideal concept. We will never be able to implement an ideal filter. Okay, so this is also a practical issue for you to keep in mind. You can never implement an impulse response that lasts from minus infinity to plus infinity. Okay? It's even not possible to store. It's not possible because going backward in time means we need to time travel. That's the meaning of convolution with a kernel which goes backward in time to infinity. You need to start convolution since dinosaur time. So it's a theoretical construction. Okay, we need to. So this is there are some practical issues right here. Okay, so that goes there. Yeah, ideal low-pass filter can never be realized. That's an issue that goes right there. For D to A conversion, we know that we need. Ideally, we want that filter, that sinc filter, but it cannot be realized. And then the third practical issue is something that we can touch on. Okay, so ideal continuous time to discrete time conversion is approximated by analog to digital, so that we can represent numbers by zeros and ones. Okay, so this is a practical issue, and we will focus on this issue. Okay, but before we do that, I want to draw a picture of what anti-aliasing filter is about. Okay, so let's see an example. Let's say if our signal in the frequency domain has broadband. Okay, broadband. has a broad bandwidth, which extends beyond, let's take audio as an example. If our signal extends beyond, let's say, 20 kilohertz, that's the upper limit. That's the upper limit of our hearing, right? For humans, most of us hear only to 20 kilohertz. Okay, you cannot hear more higher than that. So this is an example when we, let's say, when the signal has some high frequency component, maybe due to a bat, yeah, some animal sounds, yeah, some animal sound that goes here. So the idea is very simple. We want to reject, there are two things. We want to reject, if all we care, if our sampling period, if our sampling frequency is, this is actually a kind of standard, 48 kilohertz. That's a pretty commonly used standard for audio processing, digital audio. Let's say the sampling rate is 48 kilohertz, okay? So we want to reject, we want to apply an anti-aliasing filter that may look like this. Constant gain for the hearing range, okay? So from minus 20 kHz to plus 20 kHz, it has some constant gain, and then it drops very rapidly to zero, okay? Rapidly to zero, rapidly to zero, and then practically it stays practically. I mean, the gain can be ignored for the stop band, okay? An anti-aliasing filter might look like this. To ensure that anything above half our sampling rate will be negligible, 可以忽略的, anything above half of our sampling rate, to ensure that they are negligible after anti-aliasing, right? So we want any, let's say this is the Nyquist. 24 kilohertz becomes our Nyquist rate, and we can design an analog filter and which has negligible gain. If we can design a filter H, which is denoted as H of anti-aliasing filter, okay? So the design criterion for an anti-aliasing filter denoted as AA, okay? Anti-aliasing filter, we want the gain to be approximately zero for any omega bigger than 2 pi times 24 kilohertz. That's the idea for audio applications, okay? So if the filter satisfies this nice property right here, then after filtering, anything above 24 kilohertz will become negligible. Therefore, therefore you can feel free to sample the signal at 48 kilohertz. Okay, that's approximately the story. Okay? That's really, if I describe the story in a kind of in a brief way, this is what's going on. We recommend sampling fast enough, but in case our signal itself extends beyond our interest, having animal sounds, then we want to apply an analog filter whose function is to reject aliasing, and we call that filter the anti-aliasing filter. Okay, and its response may look like something like this: nearly constant gain for the passband, and the gain drops rapidly to zero, and so that the gain is negligible for the stop band. Okay, well, you can do that. There are ways to do that. If you're interested, take analog circuit design. Okay, there are ways to design low-pass filters in the analog domain. Okay, beyond the scope of this course, right? So this slide introduces anti-aliasing filter. We need to do that, and so here are a few summary items. First, I'll just read it. Anti-aliasing filter needs to begin to roll off at the frequency close to Nyquist. This is what I mentioned. To decay, the gain needs to go down rapidly, and this going down is called roll off. Roll off, 滚出去. Need to 滚出去 rapidly at frequencies starting at near Nyquist frequency. 滚出去, roll off. Yeah. Second point, this is kind of, I'll just read it. Sharp, analog filters with sharp cutoff turns out are hard to design. Please attend analog circuit design course, or some of you might have done that in the previous semester. Low pass filter is not hard to design, so there are tons of design criteria. And frankly speaking, I'm not an expert in this, so I'll just skip this point. And third point, sometimes the variable sampling rate is desired, and this is interesting. This is interesting, okay? So in certain like sound card, sound card, right? 音效卡, you can specify your sampling period, okay? You can specify your sampling period as either, let's say, 48 kilohertz or double that, 96 kilohertz, or lower than that, 22 kilohertz. You can specify your sampling rate. So, so this this may lead to some design issues. So the question is, then, do we need separate anti-aliasing filters depending upon the sampling rate? Okay? So for every sampling rate, you might need to have something available, have an anti-aliasing filter whose cutoff frequency is near half of the sampling rate. Okay? So that might be some practical issues to consider right here, but we are not going to emphasize those. Okay? Now, so next topic is finally A to D conversion. Okay, so we'll start our journey of A to D conversion. Okay? Now, so now we break A to D. A stands for analog, and D is now digital. Okay? Finally, we talk about analog to digital. So to perform analog to digital conversion, we can imagine two steps. One is to sample. We call that we want to sample and hold our signal. Sample and hold. Okay? So here is a kind of a illustration. When we have a signal that happens smoothly in time, and our sampling rate is fast enough, okay? So we're going to measure our signal right here, and right here, and right here, there, right here. And this is the action of sampling. We know that. Okay? Let me actually draw a permanent line. Sampling, sampling, okay? Sampling, sampling. We have done that before. Okay? We know what's going on. To sample our signal. But then we also need to hold. Why? Because we need time. We need time to convert the value with real numbers into zeros and ones. So we need some time. We need to finish our representation within a short time. It can be short, yeah, sure. Now electronics can work really rapidly, but still we need to somehow be able to hold the signal so that during this time, we can quantize. We can perform quantization. Okay, so that's simply explaining why we need to sample and then hold. Hold it at constant value. Okay, maybe using a capacitor. Okay, using some kind of capacitor to hold our signal right there, so that we have sufficient time for quantization. Okay, so that's the meaning of sample and hold. So now, after sample and hold, then we have this period of time, during which we can finally perform A to D, the actual conversion. We can start to think about how to represent these real numbers, the real numbers. We have time to represent the real numbers into zeros and ones. Okay, is that clear? Sample and hold. Okay? Practically, because we need time. We need time. Okay, so, all right, so in this next slide, we are going to kind of start talking about quantization. Okay, we're going to start talking about quantization. So the idea is that when after sample and hold, so right here, things are not digital yet, okay? These are still real numbers, okay? But then we have time to represent our real numbers to sort of perform rounding. Okay, rounding. 四舍五入啊，简单来讲啊。In the next slide, we'll show that this action of quantization really is rounding the numbers. It's all about rounding the number to the nearest integer. Okay, so in Chinese, it is 四舍五入. It's very simple. 四舍五入. Keep in mind. What we're going to introduce next, quantization means rounding. Rounding the number to the nearest integer points. Now we call the result x hat. Okay, we call the result x hat because hat, whenever we have hat denotes an approximation. Okay, now we have x hat, which is essentially an approximation. An approximation of our original sample values. Okay, the values that we are holding. Okay, now we are approximating them by rounding the values to the nearest integer. Okay, and with that, let me also introduce a notation. Practically, we need to confine our output to a range, symmetrically to a range, to within a range of minus xm to plus xm. Okay, practically because you cannot handle a signal that is too large. So any amplitude that is too large we will need to compromise. We cannot allow signal to go too large. Okay, so we need to confine the range of our signal, how the sample value can actually be encoded after quantization, encoding. Okay, this is about representing the numbers by zeros and ones. But we need to kind of agree that there is a finite range in which we can process our signal. Okay, anything that's beyond plus or minus xm will be rejected in one way or another. Okay, so we need to agree. So we talk about that. It will become clearer. So we need to introduce a range, and this range sometimes is called a full scale. Full scale is 2 times xm because we have positive and negative. Okay, both polarities. Okay, positive and negative. The full range, sometimes we refer to 2 times xm, the maximum value, as 2 times that as our full range. Okay, our signal is our interest will be confined between minus xm and plus xm. Okay, there's a full scale, and so the next thing is not that important. So after encoding it with binary numbers, it turns out that you can think of the representation as a number that's on one hand is quantized, and on the other hand its range is between plus or minus 1. There's a normalization. Okay, so here this coder performs normalization. And I also want to mention MATLAB. So if you actually go back to your homework number 1 and take a look of your signal, you'll find that in MATLAB at least, okay, in MATLAB just they agree to represent the audio signal between -1 and +1. Yeah, if you're interested, go back and check your signal. Just print it out. All the samples are between -1 and +1. It's just a matter of normalization. Okay, normalization. Okay, so with that, now we can finally introduce this I/O function of quantization. Okay, here we're looking at a plot, and we see kind of a shape of a staircase, sort of. Oh, no. So we are looking at staircase. Staircase, and this is an I/O function. The input is any x. Okay, the horizontal axis will be the, let's say, analog input at any time. Okay, the input, and the output after quantization can have only finitely many different values. Let me say that again. After quantization, then our signals can have one of the finitely many values. Okay? So this Q stands for quantization. Q stands for quantization, and our output is denoted as Q of X, okay? X hat might be a bit too small. Output is quantized, so that its value can only be integer multiples of big delta. So here we have some notation. If you look at the I/O function, okay, so the output can only be 1 delta, 2 delta, 3 delta, 0, or minus delta, minus 2 delta, and so on. The most negative value we can have right here is minus 4 delta if we use 3 bits. If we use 3 bits, we can have only 8 different values, right? So are we looking at 8 different values? Yes, from minus 4 to plus 3. So it is as simple as that. Okay? When we use 3 bits to represent our numbers, then we can have only 8 different possible values. And in this case, delta, they are minus 4 to plus 3 times delta. And delta has a name. Delta is called the quantization step size. 集距 step size. Quantization step size. Let me write it down. It's called the step size. And our full range right here is 2 times. This xm is, let's say, xm. What is xm? So full scale. Let me say xm is full scale. 2 times that is the full range. Okay. So I/O function. So as I said, this I/O function has 2 features. Okay. Let's take a look at this. This I/O function has 2 features. First, the output is quantized. Okay. So essentially, we are rounding to the nearest integer, so to speak. For example, anything that is in between minus half of delta and half of delta, anything in this range is quantized to 0, becomes 0. And anything that's between 0.5 and 1.5 is quantized to 1, right? Anything that's between 1.5 and 2.5 is quantized to 2. This is essentially just rounding, very easy. We all learned that. It's a 45 rule, rounding the number to the nearest integer multiple of our step size. Okay? Essentially, it's just rounding. It's very simple. So that's the first feature we want to understand. Quantization is about rounding to the nearest integer. Okay? Second feature is clipping. Anything that's larger than the largest value, unfortunately, I'm sorry. We say we are sorry. We cannot represent this number. Okay? It will saturate. We can only represent it as 3 times delta because the things are going to run out of our range. Okay? Negatively, also, anything that's more negative than minus 3.5, 负 3.5, 比负 3.5. Anything that's smaller than minus 3.5 we'll say, again, we are sorry. We cannot represent that number. It will saturate and be represented as what? As minus 4. Is that fair? Because we are only 3 bits, right? 双手一摊就是摆烂啊. So we cannot do anything better than that. Is that clear? So 2 features. Rounding the numbers to the nearest integer and then saturation. Anything outside the range of minus 4 to 4.5 to 3, we are sorry. We cannot represent them. Okay? There's no way to encode the number because when the values are too large. Okay? Right, so that's simple enough. But then there's a question of, of course, now we have 8 steps. 1, 2, 3, 4, 5, 6, 7, 8 steps. But how do we encode them into numbers? So here, so next time when we meet, next week, we'll start from here. So it turns out that we have some schemes, 有不同的策略啊, different schemes to represent A step, to assign the A step into 8 different strings, okay, 2 to the third. 2的3次方, 2 to the third. When we have 3 bits, we have 8 possibilities. But how best to encode them? We'll leave it to next week, okay? So tomorrow when we come back, please prepare for the the follow-up discussion. Okay, tomorrow will be our follow-up discussion. So the TAs, do you have something to announce? Okay, and how about the sign up? Okay, so do you get the link for signing up? Sign up. Yeah. 你解释一下。Yeah. Do you all receive the link for so you can sign up for tomorrow's for being a volunteer? Last week we have thank you very much for enthusiastically volunteering, but this week let's try signing up first. 好吗? If you have any question regarding that, 有什么问题的话, please ask the TA. Okay, please ask the TA. So otherwise, the class dismissed, and thank you for being here. See you tomorrow.
这个 exposure 跟这个是一样的意思。